Hello guys, am I audible? Okay, I guess that I should be audible now. Let me just make sure that the sound is enough. Okay, now I should be audible. How's it going guys? Good evening. In here it's still morning. Oh, echo? Really? How is that possible? How is that possible? Hello guys, so happy to see you again. Do I still have echo? That's weird. That is weird. That's me. What about you now? Still we have echo. Where are you from? I'm from Iran. Where do I look like to be from? We've explained DFS in our last session, but today we're gonna continue it and we're gonna still use it. So maybe there's something that I can fix here. Okay, now the quality must be better. Is everything fine now or not? Today we're going to talk about bipartite graphs and finding distances in graphs, in unweighted graphs, and then we're going to solve some problems from them. It's weird that we are. Let me check it myself. Wait a second. Okay, now you should be able to hear me without any issues. So, can you please confirm? I changed some things. Now good? Okay, nice, awesome. So yeah, as I said, today we're gonna talk about bipartite graphs. We're gonna use DFS again. How many of you guys have watched graph 1 before? Have you guys watched it? If you have watched it, put a plus. If you haven't yet watched it, put a minus, please. Okay, good. Have you learned everything that you discussed there, or do you have any issues with any of the topics that you discussed? And guys, feel free to join for further discussion. Feel free to join our Telegram channel here or our Discord server here. Okay. Yes, I can do that. I can drop some questions or add some sources to practice. Okay. So let's start talking about these things. So am I still muted? Or can you hear me now? Thank you guys for letting me know. If there was any issue, please let me know again. Okay, so bipartite graphs, as I discussed previously, bipartite graphs are a type of graphs that we can split all the vertices into two parts like S and T, such that each vertex from S will only have edge to vertices from T, and each vertex from T will only have edges to vertices in S. So we say that a graph is bipartite if we can split them into two parts, such that each part only has edges to the other part, not to the parts to its own part. So for example, if you have a graph like this, for example, and an edge to, for example, here, for example. Well, this is a bipartite graph because, for example, I can put these vertices in the first part and these vertices in the second part, for example. Then you see that all the red vertices only have edges to the blue vertices, and all the blue vertices have only edges to the red vertices. So a bipartite graph is a graph that I can split all their vertices into two parts, such that each part only has edges to the other part. Okay. Yes, no connection with own part, exactly. So we need to be able to split them in a way into two parts in a way that there will be no edge from a vertex to its own parts. Hi. Is it clear? If it is clear, please use this emoji or put a plus. Yes, it's called also two color. So you want to put two colors such that each vertex only has a color to the other, only has an edge to the other color. Okay, nice. You're welcome. So yes, so each of the vertices should only have edges to the other color. For instance, this graph, this triangle can in no way be, its vertices can in no way be split into two parts such that each vertex has colors, has edges to the same, to the other parts. Because anyway, in any way that you assign colors to these three vertices, in any way, you have two colors, or you have two parts, and you have three vertices. So two of them will end up in the same parts at the end of the day. Whatever you do, two of these vertices will end up in the same parts, and they have an edge to each other. So you cannot do anything. So whatever you do, these two vertices will be in the, two of the vertices, 2 out of 3 vertices will end up into the same parts, and therefore they have an edge to each other. So this graph is not bipartite. Is it clear? So we can say that a graph is bipartite if there is a way to split the vertices. There is a way. There is a graph. A graph is bipartite if and only if there is a way to split the vertices into two groups in a way that each vertex only has edges to the other group. Okay. So this is the definition of a bipartite graph. Okay. So now let's take a look at some examples. For example, we saw that this graph was bipartite, but this graph was not bipartite. Let's now consider this graph. Is this one bipartite or not? Can you please tell me that if it is bipartite or not? Yeah, we will discuss that. Your question will be discussed. How it is bipartite? How can I split it into two groups? Diagonal elements. Yes, nice. For example, I can put these two in the first group. For example, assume that one of the groups is the red group and one of them is the blue group. This is these two vertices can be red, these two vertices can be blue. So we can say that it's alternatively red and blue. Each vertices will be colored alternatively with red and blue. But what about this one? Is this one also a bipartite graph? Can I split it into two parts such that each vertex has only edges to the other parts? No. Can you say why? Why not? Why it is not bipartite? Yes, it is an odd cycle. It has 5 edges, but why it is not bipartite? It has 5. It's a cycle with 5 vertices. I see. So yes, exactly as you say. For example, this one has a color. This one has a color. For example, let's say that its color is blue, for example. Then the next one, or let's say that it is color 1. We don't know what color 1 is. Let's just name the color that this vertex has to be color 1. But the point is that the next vertex should have color 2, because it cannot have color 1 anymore. Because this one had color 1, so this one needs to have another color. Otherwise, there will be 2 vertices in the same part, in part number 1, that they have an edge to each other. It is impossible. So the second vertex should have color 2. We don't know what 1 and 2 is. We are just showing that they are different. And then this one again should have color 1, because otherwise it is in the same parts with the previous vertex and they have an edge to each other. And this one again should be color 2. Now if you consider this one, it cannot be 1 and it cannot be 2 as well. It cannot be any of them. So here we have a dead end. We cannot do anything. We're stuck. So there's nothing that we can do in here. Therefore, we can say that this graph is not bipartite. There's no way that we can color them into 2 colors such that each vertex only has an edge to the vertices of the other color. Okay, now what if I have a cycle of length 6? Assume that I have a cycle this time of length 6, like this. Is this one bipartite or not? Yeah, as you said, it is gonna be bipartite, because again I can put these ones to be red and these ones to be blue. Again you see that they must be alternatively red and blue. So whatever this is, this one should not be that. I mean, whatever is the color of the first vertex, the color of the second vertex should not be that. And the color of the third vertex should not be the color of the second vertex. So it should be equal to the color of the first vertex. So we see that alternatively they will change. But again, if we consider that we have 7 edges, I mean the length of our cycle is 7. Again, we see that we're going to be stuck, because assume that this is color 1, then this one must be color 2, then this one must be color 1, then this one will be color 2. I mean, by showing 1, I'm saying that it is either blue or red. I don't know that. Just name that as 1. 1 is like a variable. I mean, that is color 1. I mean, color 1 can be red or blue. I'm saying that this is one of the colors. This is the other one. Again, this one is the color that the one here was. This one is the other one. Again, this one is color 1, this one is color 2. Again, this one cannot be 1 and cannot be 2, and we are stuck. So what is the fact that you can say in here? What pattern do you see in here? What is the pattern that we can see in here? What can be our conclusion? What do you think the pattern is in here? This graph can be used. I don't get it, but what do you mean by 2 elements? Exactly. A cycle or a circle with odd vertices, r vertices, is not a bipartite graph. So we are just talking for now about the cycles. As we see the pattern, if we just consider, let's just consider cycles. The pattern that we see is that if the length of, if the length of the cycle is even, we see that it is bipartite. It is bipartite. Because we can just alternatively put red and blue on it. Otherwise, if the length of the cycle is odd, we see that it is not bipartite because we're going to be stuck on the last vertex. In all the other vertices, in the n-1 first vertices, they are alternatively 1 and 2. But for the last vertex, one of the neighbors is 1, one of the neighbors is 2. So we have no choice for this last vertex. And there's nothing we can do. So it is not bipartite. So now what we want to say is this. Let's talk about general graphs. So we just considered all the cycles. Now let's just talk about general graphs. Can you say any fact about general graphs now? I mean, I don't want you to tell me the final answer. I'm saying that just by what we said, you can say a fact. You can tell me a fact about general graphs as well. You can extend what we said to general graphs. You can say that there is a condition that if that condition happens, then our graph is not bipartite. We will talk about that as well. We will talk about how to detect cycles, etc. Exactly. What we can say, our fact can be this. If our graph has an odd cycle, it is not bipartite. Assume that we have a graph. The graph can be anything, but in some part of it, there is an odd cycle. So assume that our graph is this. Our graph is, for example, this. There are several other edges as well. So there are several edges in here, and we don't care about it. There are a lot of edges in here. In the middle of it, there is an odd cycle. We can find this cycle of, for example, of length 5 in the middle of this graph. So what we can say in here is that even if you ignore all the other vertices, assume that there is a good way to color all the other vertices. What you want to do with these 5 vertices? Anyway, at the end of the day, when you consider these 5 vertices, you know that in these 5 vertices, these 2 must be different. So if this is color 1, this must be color 2. Again, this one must be color 1. Again, this one must be color 2. Again, this one is color 1. And these 2 are adjacent. Or I can say that this last one, because of this one, must be color 1. Because of this one, must be color 2, which is a contradiction. So again, you are stuck in the last vertex. So it doesn't matter that if you have more edges and more vertices. If you can find an odd cycle in the middle of your graph, then you cannot do anything with that odd cycle. Even if you solve all the other parts of the graph, even if you solve and find good colors for the rest of your graph, What you want to do with this odd cycle? About the vertices in this odd cycle, you cannot do anything with them. So if your graph has an odd cycle, if our graph has an odd cycle, then it is not bipartite. I haven't yet said anything about what happens if it does not have an odd cycle. For now, we're just saying that if it has odd cycle, then it is not bipartite. But we haven't discussed that what happens if it does not have an odd cycle so far. So for now, we're just saying that if it has odd cycle, then it is not bipartite. It is in this direction and not the other direction. Is it clear so far? So what we said is that if we have any subgraph that is an odd cycle, then we cannot do anything with that odd cycle. There's nothing that we can do with that odd cycle. Therefore, it is not bipartite. Is it clear? Nice. If it is clear, please use this emoji or say that in the chats. And feel free to ask questions if you had any questions. Yes, exactly. This is the final thing that we want to say. If there exists an odd cycle in the graph, then the graph is not a bipartite graph. Yeah, now we will discuss that what happens if there's no odd cycle. Can we say that if there's no odd cycle, then the graph is bipartite? We will discuss that. Our graph is not directional. Our graph is not directional. We are just considering our undirected graphs. The first graph live is from the beginning of the graphs? I don't understand your question. Okay. So now we know that. So as a matter of fact, we know that if we have an odd cycle, then the graph is not bipartite. So the next question is, what if there are no odd cycles? So this is the next question. What if there are no odd cycles? Well, I want to show that. What do you guess? So far, what is your intuition? Do you think that if there are no odd cycles, the graph is going to be bipartite or not? There still is other cases that the graph will not be bipartite. What do you think? So assume that there are no odd cycles. Can we say that then our graph is bipartite? Do you think we can say that? Probably no, probably yes, that is correct. Yeah, we don't know that. I'm just saying that, what is your guess? What do you guess? No? It may or may not. Okay, nice. It's good that you understand that when we prove something in one direction, about the other direction we don't know anything so far. So we showed that if there is an odd cycle, it is not bipartite. But we haven't showed that if there is no odd cycle, it is bipartite yet. But I want to show that if there are no odd cycles, then the graph is bipartite. I want to show this. So I want to show that. I want to provide an algorithm that can color all the vertices. I will say that which vertices are from group 1, which vertices are going to be in group 2. And I show that this is going to give me two groups, two parts, such that they will not have edges to themselves. how do I do that? Well, my algorithm is this. If I provide an algorithm that can split them into two parts and everything is going to be fine, then it means that it was bipartite because I find a way to partition them. The algorithm, I can run the algorithm on each connected component. So if my graph is not connected, there must be several connected components, right? I mean, either my graph is connected or it is not connected. If it is not connected, then there are some connected parts. For example, this, we have discussed about connected graphs in our last session. This is, for example, a graph, but it is not connected. But if you see, we have several connected parts. This is a connected part, this is a connected part of it, and this is a connected part of it. We call these connected parts as connected components. So we have several connected components. I run my algorithm on each connected component separately because the colors of each connected component does not affect the colors of another connected component because they have nothing to do with each other. So if I have several connected components, I can solve them independently. If I can solve each one independently, then I'm done because they won't do any harm to each other. They do not have any edge to each other. So however that I can fix each of these connected components just independently, if I can solve each connected component independently for each one of them, I have a group 1 and group 2. At the end, I can merge all the group 1s and merge all the group 2s, and then I'm good. And I have two good parts, right? So what I can do is that I can solve the problem for each connected components, and then I can merge these two groups for all of them. And they will not do any harm to each other. Do you agree with this? Is it clear so far? So I just show that if there are different connected if it is not connected, I can solve it independently for each connected component, and then the problem will be solved at the end. If I just solve each part independently, because there are no edges from any of these parts to any of these other parts. So okay, so I have a connected graph now. I have a connected components. I have a connected component, so all the vertices are connected. I have a connected component, and I want to split the vertices into two parts. So how can I do that? I can do something similar to a greedy approach. I can start from a random vertex and say that, okay, you are gonna be at group 1, and then I can say that all of its neighbors, so it's gonna be like a greedy approach. I mean, everything will be, I can find everything deterministically. I pick a random vertex, I say that, okay, you are at group 1. And then for all its neighbors, I put them in group 2. And for all the neighbors of neighbors, I put them in group 1. And so on. Again, for all the neighbors of neighbors, I'll put them on group 2 and so on. So I can run something similar to DFS. I can have, for example, DFS on vertex V, and I do this for every U on just adjacent vertices of V, all the neighbors of V. I just say this: if that vertex was already visited, this part is from normal DFS that we did in our last session. we said that if u was visited, we will just continue. And we shouldn't forget to set visited of v equal to true in here as well. And then otherwise, if u was not visited, I just say that color of u is gonna be, if color of v is 1, color of u needs to be 2. If color of v is 2, color of u must be 1, right? So if color of v is 1, color of u must be 2. If color of v is 2, color of u must be 1. So what can I say? I can say that color of u must be 3 minus color of v, right? If this one is 1, that one will be 2. If this one is 2, that one will be 1. So color of u will be 3 minus color of v. And then do DFS on u. Okay, so this is how I'm gonna do it. And this way, because it is connected, it is a connected subgraph, it is a connected component, then all the vertices will be visited. All the vertices are gonna have colors at the end of this DFS, right? Do you agree with this? So is it clear so far? We run a DFS as we saw in our previous session. When I visit a vertex, I say that visited of v is equal to true. And then for all the neighbors, if they are already visited, I will continue. I will not do anything. Otherwise, I need to do their DFS. But before doing their DFS, I set color of u equal to 3 minus color of v. And initially, I have picked a random vertex and I have called its DFS. I pick a random vertex initially, set its color to 1, and run the DFS on it. Run my DFS on it. Is everything clear so far? If you have any questions, feel free to ask. Okay, I will explain the time complexity of it as well. That was a very good question, in fact. If you have any other questions, feel free to ask. Yeah, we're gonna discuss it. That is correct. It is n plus m, but we're gonna discuss it in detail. If it is clear, please again use this emoji or say that in the chats. Otherwise, if you have any questions, let me know. Let me. Clear? Okay. So nice. We now that we have this, we're gonna have the colors on all the vertices. There is one thing that we need to show. Can you say that what is the last thing that we need to do? Just think about it for a second, that what is the last thing that we need to do. I will come back in a second. I'll come back in a second. Okay, sorry for that. I had to leave for a second. So can you say that what is the thing that I need to check at the end? What is the final thing that I need to check? I need to ensure that my graph is bipartite. right? DFS and BFS both work here. I mean, they have no difference. DFS is a bit simpler because you don't need to define any additional values like Q, etc. And even the visited array that we defined can be removed. I will talk about that. And right now we only know DFS. We haven't yet discussed BFS, but both works. I personally prefer DFS, but both works. Yes. Nice. So, do you agree that I want to show that I want to. So I assume that my graph has no odd cycles. I want to show that if my graph has had no cycles, no odd cycles, I mean. No odd cycles, then my groups are fine. The groups that I made are fine. I mean, there's no edge from a vertex of a group from another vertex of the same group. How can I say that? I just want to say the proof. Now, I'm saying that, assume all the vertices that have color 1. Assume that there is an edge between two vertices with color 1. Assume that there is an edge between these two vertices. So there are two ways. If it is bad, either there must be an edge between two vertices of color 1 or two vertices of color 2. But what happens? Well, do you agree that when we did this, I mean, we set 1 as root. We set one vertex as root, and then we set the color of the children. This vertex has color 1. These vertices have color 2, and then the children of these, if they are not visited yet, they're gonna have color 1 again. Then the children of it again have color 2. Then the children have color 1, and so on. If you see, you can find the pattern that all the vertices have color 1 are at even heights. I mean, this is height 0, this is height 1, this is height 2, this is height 3, this is height 4. I mean, if you consider the distance from the roots, I mean, you can just say that in what heights they were called. For example, if their parent was in this height, their height is going to be 1 more than that. So if you see that what is their height compared to the roots, vertices that have 1 in them are at even heights in the tree that DFS will give me. I mean, if you just consider the edges that DFS has, this will give me a tree. And in this tree, all the vertices with color 1 have even distance from the roots, and all the vertices with 2 have odd distances from the roots. So what I can say is that both these vertices have even distances to the roots. Maybe some part of their path intersects, but anyway, their distance to the roots, I mean, this part is even, and this part is also even. And maybe some part of it is intersection, and it will be counted twice. Because this part is counted twice, it has no effect on parity. I mean, these edges here will be counted twice, so no effect on parity. So I can say that we have a cycle in here with an odd length, if that happens. Why? Because there was an edge here, and then the rest of it has even number of vertices, because there are even edges here. Even edges here, so in total I have even edges, and this part is counted twice, so has no effect on parity. So I can also say that it's like this part has even edges. So it's like between these two ones there is a path of even length, and when I add another edge to them, it means that there was an odd length cycle. So it means that If there is an edge between two ones, then should have been an odd length cycle, which is a contradiction because we assume that there is no odd length cycle. And also, you can say the same thing if we have an edge between two vertices with color 2. Again, we can say that the distance of both of them to the roots is odd. So if the root is here, this distance is odd, and also this distance is odd as well. So the sum of these two, if I come from here to here and then I come back from here to here, the sum of these two is even, then this part is counted twice, so it has no effect on parity. So I can say that this part is even. So what I'm saying is that the distance between two vertices of the same color is even. Therefore, when their distance is even, when you add an edge between them, they already have a path of even length between each other, I mean from one to the other one. And when you add another edge, you're going to make an odd cycle, which is a contradiction because we know that we had no odd cycle. Therefore, if there is such edge, we can say that this is a contradiction, and therefore no such edge exists. Therefore, we right now have two good groups. Does it make sense? It is okay if it doesn't completely make sense. If you have any questions, feel completely free to ask that. If you're completely okay with that, please use this emoji or put a plus. If you're not completely okay with that, say that in the chat. A graph with no cycle is always bipartite. Yes, a graph with no cycle is always bipartite. Because you can put any colors on it, and you can put any colors on it, and there is no edges between two vertices of the same color, because in fact there is no edges at all. So when there is no edges at all, there is also no edges between two vertices of the same color. Okay. Well, I'm saying that, assume that, for now it's not even that important as well. I just want you to have a clue of this proof. But later on, it's going to be a more advanced topic, and later on you will comprehend it completely. So you don't need to worry about it to comprehend it completely as of now. I just want you to have a clue of it, to understand what a bipartite graph is. This is the most important, but we're going to learn everything completely step by step, one by one in order. But for now, you need to have a clue of what a bipartite graph is. So the point is that if the graph has no cycles, I can start from one vertex and run a DFS and color all the vertices. So this vertex has color 1, these vertices in here have color 2, these vertices in here have color 1, these vertices in here have color 2, and so on. So the point is that if you consider all the vertices of color 2, they have odd, if you consider the tree that DFS will give you, DFS will give you a tree, right? If you consider the edges that you will go through them in DFS, that will give you a tree. And the point is that all the vertices at odd depth will have color 2, because the color is different to their parents. The parents is the vertex that is called their DFS. We know that roots will call the DFS of some vertices. And then each of these vertices will call the DFS of some other vertices. And then each of these vertices will run the DFS of some other vertices. And we know that there's always an edge between them. This forms a tree, right? Because each vertex we will call its DFS exactly once. We know that each vertex will be called, because this is a connected graph, the DFS of each vertex will be called, and it will also be called only once, not more than that, because once it is called, its visited will be true, and it will not be called again. So I can say that DFS can make a tree for me. I can say that this is my roots. I can see that DFS of which vertices is called by the roots. And then each one of them will call DFS of some other vertices. And then each one of those will call DFS of some other vertices. Let's have an example. So assume that this is my graph. This is the graph I have. So assume that this is my graph. This is vertex 1, 2, 3, 4, 5. Let's change the numbers so that it's more randomly. 7, 8. Okay, so this is my graph. I mean, if we run a DFS on the first vertex, vertex 1 first calls DFS of vertex 2. So from 1 I will go to 2. Then vertex 2 will call the DFS of vertex 6. So I put an edge between 2 and 6. So from 1 I will go to 2, and then from 2 I will go to 6. Then from 6 there's nowhere that I can go, so I come back to 2. From 2 there's nowhere I can go, so I come back to 1. Then from 1 again I can go to 4. So I put 4 in here. 4 DFS of 4 is called from 1. Vertex 1 has called the DFS of vertex 1. Again from 4 there's nothing else I can call, so I come back. Then I will call DFS of vertex 5 from vertex 1. So vertex 1 will also call vertex 5. And you see that vertex 1 will not call vertex 6 anymore because it is called once before. 6 is called by 2. So 1 will not call that anymore because it is now visited. Then from 5 I can call DFS of vertex 7. From 7 I can call 3. From 3 I can call 8. And then from 8 there's nothing to call, so I come back. So from 5 I will call 7. Then from 7 I will call 8. From 8 I will call 3. Right? So this gives me this form of a graph. And I can say that what I'm saying is that if you consider the colors that we give the vertices, this gives me some form. I will define tree in more details later on, but I'm saying that this will give me something that I can say that in here all the vertices, I mean when I want to put the colors, for example in here I had an odd cycle, so this is not the example that we're gonna run DFS on it. But when we don't have an odd cycle, when we have this structure, this sort of a structure, this can be anyway. For example, this vertex has called these ones, then these ones has called these ones, and so on. You see that all vertices that have one, they have an even distance to the roots. All the vertices have 2, they have an odd distance to the roots. I mean, where they are, because you can see that each time the color is flipped. So it must be flipped even number of times that it is 1 again. And it must be flipped odd number of times that it is not 2. So you can say that the distance, I mean if you consider this shape, this graph that you have in here, if you only consider the edges that are called in my DFS, when you have 2 vertices with color 1, I can say that their distance is going to be even because both of them are have an even distance to the roots. Both of them have an even distance to the roots. So the sum of these 2 values, if I come to the roots and then I come back to this vertex, this is going to be an even number. Now this part is counted twice, so I can remove it for now. I mean, it has no effect on parity. So I can say that this distance between them has an even length. When I add an edge between them, this will form an odd cycle. Also, if there are 2 vertices with 2, they will also form, because both of them have an odd distance from the roots, I mean, it is toggled odd number of times that there are 2. If I come from here to the roots and then I come back to this one, then I have even number of edges. But now I can now remove this part because it has no effect on parity. I mean, because this was odd and this was odd, the sum of them is even. So this part is also even. When I add an edge, I have an odd cycle. Okay, does it make sense now? I mean, it's okay if you do not completely comprehend it for now. The key points that I want you to get from this part, we will get back to prove it completely later on. But I just wanted to familiarize you with the definition of bipartite graphs. So a graph, we get back to the details and the proofs once again when we in a more advanced state. We will come back in the next streams. We will come back and we will completely understand. But for now, I want you to build an intuition about the bipartite graphs. It is okay if you do not completely understand the whole proof as well. I mean, we have to go on all the topics one by one. So for now, you just need to know what a bipartite graph is. So a bipartite graph is a graph that I can split it into two parts such that all the edges are from a part to another part. There's no edge from a part to itself. We don't have these type of edges. It is possible to split it into two parts such that in each part all the edges from each part is from to the other part. There's no edge from a part to itself. And if we have an odd cycle, it is not bipartite. My graph is not bipartite. There's no way to split it into two parts. And if there is, it does not have odd cycle. If it has no odd cycle, then it is bipartite. This part was easy to show. This part also, we proved this, but we will come back to this proof once again. But I just want you to ensure that you know this. I mean, this is the bipartite graph. You just need to be familiar with yourself with the definition of bipartite graphs for now. Is it clear completely? We will solve problems today. It depends on how much time we will have, but there are some problems that I want to discuss. We will see that how much time we will have to discuss them and how many of them we can discuss today. If it is clear so far, please use this emoji or put a plus. If it is not, also put a minus or let me know, ask any questions. So I hope that you've built some intuition about bipartite graphs. And we're going to use it very soon. Nice. Nice. Very good. So, this was about bipartite graph. We will get back to them very soon. And now I want to discuss another thing as well. Let's assume that we have an undirected for now. So let's just consider the simplest form of the graphs, undirected, unweighted graph. Okay, assume that we have an undirected, unweighted graph. I want to find the distance from a vertex to another vertex. And what is the distance? In order to define distance, first I need to define some other words as well. We should get familiar with terminology of the graphs. There are some definitions like path and walk. Well, in a graph, a walk on a graph is gonna be if we start from a vertex and traverse the edges one by one in any order. And I mean they must just be consecutive. For example, if we start from here, then we use this edge to go to here, then we go here. Assume that it is a city, and these are its junctions. It's like we start from this junction and we just walk over all these passes between the junctions, all these, for example, roads or anything. So this is a walk, and we can come back to the same junction many times. We can go over the same edge many times. So this is a walk. It's just we start from somewhere and we walk over the graph. This is going to be defined as a walk. So a walk can be like this. Let me also show you an example of a walk. So if this is our graph, this is 1, 2, 3, 4, 5, 6, 7, and 8. For example, a walk in here is that if we start, for example, from vertex 2, we can start from 2, go to 4, then go to 3, then go to 5, then come back to 4, then go to 3, then go to 5, then to 7, then to 8, then to 5, then to 3 again, and then to 1. This is a walk. So it means that we start from here, from this 2. From 2 we come to 4. Then from 4 to 3. From 3 to 5. Again to 4. Again to 3. And then again to 5. Then to 7. Then to 8. Then to 5 again. Then to 3. And then to 1. So it's like we have started from somewhere and we are just doing a walk. This is the definition of a walk. Is the definition of a walk clear? If it is clear, please again use this emoji or tell me in the chat. You need to get familiar with this terminology. We're going to use these words a lot. I mean, in graphs, these words are going to be used a lot. So make sure that you're completely okay with them. Endpoints of the walk, they're not set. They can be anywhere. A walk, yes, a walk is if we start from a vertex in our graph and we just start walking. From 2 I go to 4, then from 4 I go to 5, then to 3, then to, for example, 5, then to 4, and so on. So I start from some, this is, for example, a walk as I showed here. If I start from a vertex and I go over all the vertices one by one. Now, can you say that what is the definition of a path? So now we know the definition of a walk. So what is a path? What is a path then? A path is a walk. A path is a walk without any duplicated vertices and edges. So a path is a walk, but the only difference is that, I mean, every path is a walk. So every path is like passes are a subset of all the walks. So every path is also a walk, but every walk is not necessarily a path. So it's like walks, the set of all the possible walks is a superset of the set of all the possible passes. Right? So every path is also a walk, and every walk is not necessarily a path. A path, for example, in here, if you see, we first go from 2 to 4, then from 4 to 3, then from 3 to 5, and then from 5 back to 4 again. This is not acceptable in a path. In a path, you cannot go to the same vertex twice or to the same edge twice. Each edge and each vertex must be visited only once in a path. So a path in this graph can be like this, like going from 3 to 5 to 7 to 8. This is a path. If you see each vertex is visited once, each edge is only visited once. So we do not have any duplicated vertices or edges. Is this one also clear? 1, 3, 4, 2, 1 is not a path. In fact, that is a cycle, and that's the next thing that I want to tell you about. 1, 3, 4, 2, 1 is a cycle. It's not a path because it has duplicated vertices. Okay. Now the next thing is cycle. A cycle, as you said, is gonna be a set of vertices. I mean, again, we cannot have duplicated vertices or edges. Only the first vertex and the last vertex are the same, because at the end we want to get back to where we were. So we start from a vertex and we will visit the vertices and edges. We will visit each vertex and each edge only once. The only thing is that at the end we will come back to where we were. Still, we cannot visit the same vertex twice. Only the last vertex is the same as the first vertex, but in the middle of it we cannot visit any of these vertices more than once. Only once, and this vertex itself cannot be visited as well. So the point is that a cycle still is going to be a closed path that's no vertex and no edge is visited more than once. So even the first vertex that we are visiting it at first and at the end, if you consider it as a closed path, it's like that is also visited once as well. So, for example, the example that you said that we have, for example, 1, 3, 4, 2, 1. This example. Let me just clear this part. This example that you had, you said that we go from 1 to 3 and then to 4 and then to 1, then to 2 and then to 1. This example. This is a cycle because this is a closed path, and even this vertex 1, even though it looks like we are visiting it twice, but if you look at it like a closed path, because if they are at the end and at the beginning, they are the same thing. So it's a cycle. You see that we have a cycle. Each vertex and each edge is visited only once, and it is closed. Is this also clear? Is the definition of cycle also clear? If it is, please again use this emoji, and thank you a lot, guys. Or say in the chats. A trail that finishes on the vertex, it begins on. Right, exactly. Now no vertex is repeated. Yes. Yes, a circuit is the same that vertices can be repeated, but it is not very useful in our definitions. But yes, so there were 3 things that you need to completely understand. So these are very important. So one of them was a walk, a path, and a cycle. You need to make sure that you're completely familiar with all these 3. You need to make sure that you're completely familiar with all these 3. These are very, very important. Walk, path, and cycle. So now let's say that, what do we mean by distance then? Distance of 2 vertices, u and v. The distance between u and v is the length of the shortest path from U to V. So the distance of U and V is the length of the shortest path from U to V. Okay. So what do I mean? For example, if you consider this graph, what is going to be the distance between 3 and 7? What is the distance between 3 and 7 in this graph? Do you know this? Exactly, 2. For example, there is one path to go from 3 to 5 and then from 5 to 7. There is also a path to go from 3 to 5, from 5 to 8 and from 8 to 7. There is also a way to go from 3 to 1, then from 1 to 2, from 2 to 4, from 4 to 5, and then from 5 to 8, for example, and then from 8 to 7. So we have all these passes from 3 to 7. But we want the shortest path. So we have all these passes from 3 to 7, but what we care about is the shortest path. The shortest path has 2 edges. So its length is 2. I mean, I have to traverse 2 edges to get from 3 to 7 in my shortest path. So the distance between 3 to 7 is 2. For example, you can look at it like this. I mean, for example, assume that we are at vertex at junction 3 and we want to go to junction 7. And my graph is unweighted. So assume that each road takes exactly 1 minute. It takes 2 minutes from me to go from vertex 3 to vertex 7. So I can look at the distance between 3 and 7 as 2. Because if I'm late and I want to go from 3 to 7, then I can go there in 2 minutes. Right? So the distance is defined like this. Is this also very clear? Okay, nice. So this is how we can define. This is how we can define the shortest path. Now the question is that how to calculate the shortest path. How to calculate the shortest path. Let's for now say from 1 to n. From vertex 1 to vertex n. How to calculate this shortest path? Well, there is one way to do that, and it is like this. Well, we can start from vertex 1 and each time I can define an array of distances. Distance of vertex, distance of V. I mean, it's similar to what we did in DP. In DP, we said that instead of solving one problem, we define so many subproblems and we try to solve all of them. Instead of just solving that one problem, we will try to define several subproblems and solve all of them. That's the same thing that I want to do in here. Instead of just finding the shortest path from 1 to n, let's find all the shortest passes. Let's find for every v the shortest path from 1 to v. So what I'm trying to do is that instead of just solving it from 1 to n, I want to find the shortest path from each vertex, from vertex 1 to each vertex v. And I call it as d stuff v. It's an array named this. D stuff v shows that what is the distance if I start from vertex 1 and I go to every vertex like vertex v. Well, in here the point is that when I start from vertex 1, can you say that what is the base case here? Let's just solve it together. Can you help me and let's find out what are the distances. Can you say that what is going to be our base case here? I mean, what is the first vertex that I know its distance? I know the distance from vertex 1 to this vertex. Yes, 0 distance from 1 to 1, right? So this stuff, 1 itself is 0. Because the distance from vertex 1 to vertex 1 is 0. Do you agree? So as the base case, I know that this stuff 1 is 0. So the point is that I can start from vertex 1 and I can put all the neighbors of vertex 1. I can say that all the neighbors of vertex 1 have distance 1. So vertex 1 itself has distance 0. All the neighbors of vertex 1 have distance 1. Then all the neighbors of vertex 1 have distance 2. Then all the neighbors of neighbors have distance 3. And so on. So if I go forward, I can find the distances from the roots to all these vertices. So vertex 1 as the root has distance 0. And all the neighbors of vertex 1 have distance 1. All the neighbors of neighbors have distance 2. All the neighbors of neighbors have distance 3, and so on. Right? The graph is unweighted. We don't have any weights. So what I can do is this. I want to implement a code that can do this. For vertex 1, it can just store all its neighbors somewhere and set their distance to be 1. Then for the neighbors, I want it to call the neighbors of the neighbors for each of these neighbors. I want to go over them and call their neighbors and set their distance to be 2. Because I'm sure that their distance was not 1, otherwise they were added previously. So I want to have some iterations. If I consider a vertex with distance I consider its neighbors. Let's say that the ID of this vertex is I and its distance is d stuff I. Okay, so assume that I have vertex I and its distance is d stuff I. Then all its neighbors, if I don't know their distances yet, it means that their distances must be more than this. So let's use an easier names. So let's say that it was vertex V and its distance was I. I is the distance. So I'm saying that all its neighbors will have distances at most I plus 1. And if they already do not have any distances, it means that they were not good enough to have distance I. Because, for example, at first, vertex 1 has distance 0. Now if I consider its neighbors, none of them could have distance as 0 because only for 1 itself its distance was 0. So I will set all of them to be 1. Now if I consider the neighbors of the neighbors, maybe some of them have edge to each other, and also they have an edge to this vertex with distance 0 as well. But for all the other adjacent vertices, if they were not good enough to that their distances were 0 or 1, now their distance can be 2. So for every one of them that their distance is not set yet, I set their distance to be 2. I do it for all these vertices. And again, when I come to these vertices, maybe they have some neighbors in here, some neighbors in here, but they will have some other neighbors as well. If they have a neighbor that its distance is not set yet, I need to set the distance of that neighbor to be 3. And so on. So each time when I'm on a vertex such that its distance is I, what I need to do is to visit all its neighbors that's their distance. I have to see all its neighbors that their distance is not fixed and set their distance to be I plus 1. And if they have some neighbors that their distances is already calculated, then I do nothing with them. I mean, they are already calculated, so I do not need to make any change. But even if they were not good enough that their distance is set yet, then I set their distance to be I plus 1. Is what I want to do clear? If you have any issue with that, please let me know. So I start from vertex 1 for all its neighbors that are not visited yet, I set the distance to be 1. Then from those vertices, for all their neighbors that are not visited yet and I don't know their distance, I set their distance to be 2. For the neighbors of them, I set their distance to be 3 and so on. So how do I implement it? Well, for implementation, I can define a queue. I can have a queue such that I put all these vertices in a queue. I mean, a queue is like a data structure in C++, but you can look at it as a real queue, a queue that you see in real world. That people come into the queue, and each time the first person of the queue, we do its work, we handle its work, and we do his work, and he gets out of the queue. Each time one person comes to the end of the queue and one person will pop from the first of queue. So a queue is a data structure like this. It is really like a queue in the real world. A person can come to the end of it and be added to the end of the queue, and also a person from the head of the queue, I can do his work done, and just he will get out of the queue. So what I do is this. I mean, a queue can be defined like this. You can define a queue and then write its type. For example, it's an int, and just name it. I just name it with queue itself. So I define a queue of int of queue. I just say that initially in my queue I push vertex 1 itself, and I set this stuff 1 as 0. It is 1-based indexing for simplicity of explanation, but if you know what 0-based indexing, it is better if you use 0-based indexing in your code. But that doesn't matter. If you don't know that, it doesn't matter at all. So I can do this. I can say that while queue.size was greater than 0, just do this. See that what is the vertex at the top of this queue. So v is equal to queue.top, and then I can just say that it's like the first person in the queue. Okay, it's just like the first person in the queue, and I want to handle its work. Okay, I just want to handle its work. I'm sorry, I used top but I was wrong. I just searched it to make sure that I used the word for stack. Q.front, sorry. I just see that who is at the front of the queue, and I do his work. So Q of front is the person at the front of the queue. Q.size is that how many people are in the queue. So this is Q.size. This is Q.front. And this action of adding someone to the end of the queue is as Q.push. If I say Q.push X, and X will be added to the end of your queue. So int of v is equal to Q.front, and then I say that if, let's say it like this. Then I say that I know that distance of v is set right now. Then I have a for on all the vertices adjacent to vertex v. For int of u adjacent to vertex v. I can say that if distance of u is not set yet, for example, initially I can set the distances of everything to -1, which means that it is not defined yet. So I can do this. I can mem set. This code is to set the distance of all the vertices to -1. You can also always use memset, just keep it in mind. Use memset when you want to set everything to -1 or you want to set everything to 0. For other values, do not use memsets. You will get to know that why it is special for 0 and -1, and for the rest it doesn't work properly. As a short, it's because it works with bits. But anyway, you can use memsets and set dist -1 size of dist. This way you set the distances of all the vertices as -1. And -1 means undefined. It means that it is not defined yet. I don't know their distances yet. So if distance of u was -1, it means that it is undefined yet. So it was not, it's like it was not good enough to have distances at most I. So if this is vertex v and it has dist of v, and let's say that dist of v is equal to I, then I have a u that its distance is, I don't know its distance yet. So I can now say that its distance is going to be equal to I plus 1, distance of v plus 1. I can say that if this happens, set distance of u to distance of v plus 1, set distance of u to distance of v plus 1, and then do q dot push u. Now you have to handle u as well. Okay. So this is how we're gonna find the distances. At the end, I mean when we did all these, at the end we need to just see out this stuff n, if you are looking for the distance to vertex n. And this is how we can calculate the distances to vertex n. It is possible to use fill or memsets, but these two can work when you're working with arrays. So this way you can find the shortest path from vertex 1 to vertex n. Next, I'm gonna say that why BFS does not work to find the shortest path, and I will also talk about the time complexity of them. And maybe we can do the problem solving in the next session, because it seems like we won't find enough time to do the problem solving today. But that's okay. We will have the next session, our next session to be only for problem solving. So is it clear what we did? Is what we did clear? Please tell me if you find this clear or not. So the main approach, the next session is next week. Each week we have one session. Sharon, where do you think it's best to learn DSA from? Right now you can use USACO guides, for example. That is very good, but very soon maybe I want to also cover in the live streams all the topics. So maybe in a few months this channel can be a good place to learn everything. I hope. We are in the process of covering everything. So the main idea in here was to just, we start with our queue. Initially only we put vertex 1 in our queue and we set distance of 1 to 0, and then we have a while q.size was greater than 0, we just consider q.front, and for every u as adjacent vertex of v, we set if distance of u was -1, we set its distance to be distance of v plus 1, and then we say q.push u, and at the end we just need to see out n. And this is called BFS. This idea of starting from a vertex and call all the neighbors that are not visited yet, and then from them call their neighbors, and so on. This going down level by level is called BFS. We need to talk more about the differences between DFS and BFS, and what is the concept behind DFS and what is the concept behind BFS. That is an important thing that I have a lot to say about, that what is the difference of the concepts of DFS and BFS. But for now, I think this is what you need to know. This is how BFS is gonna work. Is it clear? Thank you. I'm glad that it helped. I hope that the graph series will also help a lot. Okay, nice. So is it clear that's how BFS is used? Now I'm gonna also talk about the time complexity of them. DFS and BFS. And then we're gonna have a problem solving session next week. Hello. So, okay, about time complexity. About time complexity, well, what we can say, let's talk about the time complexity. Time complexity of both DFS and BFS. Well, in DFS, we know that we had some DFS of V. For every vertex V, we had a 4 U on adjacent vertices of V. We first say that visited of V is equal to true, and then we say that if U was not visited, if not with of U, just let's call DFS of U. This was DFS. So let's see that what was it, time complexity. Well, the point is that, do you agree that in DFS we visit every vertex only once? In DFS we visit every vertex only once, right? We will not go to the DFS of a vertex more than once. Do you agree with that? In DFS, we will go to the DFS of each vertex because next time we see that it is visited, so we will not call it. So we will visit the DFS of each vertex only once. And for the same reason, each of the edges that we see in here, each edge is between two vertices like U and V. Each edge is between two vertices like U and V. Each edge will be seen only twice, because we have DFS of U only once and we have DFS of V only once, and this edge is the edges of these two vertices. So only for these two vertices I will see this edge. I will see this edge only for these two vertices. Okay. Therefore, I can say that each edge will be seen only twice. So therefore, it's like in DFS, each vertex will be visited only once. I have n vertices, so it's going to be n plus each edge will be visited 2 times, so plus 2m. So it's like the number of operations, the sum of the length of this force is going to be 2m, and the number of times that this part will be executed is going to be n in total. So it's going to be n plus 2m. The number of operations in Atmos is going to be n plus 2m. And in order, because we do not consider these coefficients, we can say that it is from order of n plus m. About time complexity and stuff, we need to have another topic stream that we only talk about time complexity. But for now, what I want you to know about time complexity is this. We just remove the coefficients and the things that are dominated by other things. So if we have, for example, m plus m squared is more than m, so you can remove m, so it is from O of m squared. When we have n squared plus 2n plus 5m, first we remove coefficients, then we have n squared plus n plus 5m. Then we say that n squared dominates n, it's always more than n. So we remove n as well, and 5 was removed as well because it was a coefficient. So my order is going to be n squared plus m. In here, in DFS, my order is going to be n plus m because it was n plus 2m operations, and when we remove coefficients, it's going to be n plus m. Is it clear now? Is it clear that's how this time complexity can be calculated? Nice. So for DFS, the time complexity is n plus m. Also for BFS, if you look at here, again this V is only calculated only once. I mean, these parts will be executed only n times, because we will visit each vertex V only once. And then next to that, right after that, we have a 4 on all its edges. Again, for each edge is from between two vertices, like U and V. So each edge will be visited twice. Each edge, therefore, will be visited twice. Once in U and once in V. So the sum of the lengths of this force, how many times this force will be executed, this is going to be 2m. So again, we have n plus 2m, which is going to be O of n plus m. So about the time complexity of DFS and BFS, both are O of n, both are n O of n plus m, and that's going to be all. Both DFS and BFS are going to be from order of n plus m. Does it make sense? If so, I think now we can discuss one problem. That's a good thing that we can now discuss one of the problems that I wanted to discuss today. So let's talk about this problem now. I thank you very much. I recommend you to start learning CP directly by solving so many problems on CP, etc., in CF, etc. It's mostly about learning learning by solving problems, not learning by just reading books, etc. That can help, but the main thing is to just start solving problems. Nice. So now that you're ready, let's just talk about this problem, the two roots. 601A, I sent you the link in the chats. The two roots. It says that assume that we have n towns and there are m bidirectional railways. Okay, so it's like there are two types of roads. If there is a railway between them, I mean between each two towns there is a road. It's either in a railway or it is a road. Okay, so between each two vertices, it's exactly one of them. It's either a railway or it is a road. And we have a train and a bus. A train can use a railway, a bus can use a road. So between each two vertices, there is one of these two type of edges. It's either a railway or there is a road. And we have a train and a bus, they will both leave town number 1 at the same time, and they both want to get to town number n. And they do not make any stops on the way, and the train can only move along railways, and the bus can only move along the roads. Now you want to plan the routes for the train and for the bus such that, first of all, they do not visit the same vertex at the same time. They will not visit any vertex at the same time. Otherwise, they might have an accident. So they do not have to, they must not visit the same vertex at the same time. And you want to minimize the time that it takes for both of them to arrive at vertex n. Okay. So you want the minimum number of hours needed for both vehicles to reach town n. So let me explain it to you once again on tablets. What this problem is saying is this. It says that assume we have n towns. Between each two vertices, there is either a road or there is a railway. So between each two vertices, there exists exactly one of them. So it's like between each two vertices, there is either a blue edge or a red edge. Exactly one of them. Between no two edges are between no two vertices, there are both type of edges or no type of edges. There is exactly one type of edge. It's either a railway or it's a road between each two vertices. And there is a train and a bus at vertex 1. There is a train and there is a bus. Both of them want to start from here and get to vertex n. The bus can only move along the roads, and the train can only move around the railways. You want to plan the roads, they must not visit the same vertex at the same time, and you want to minimize the time that it takes for both of them to get to vertex n. You have to say that what is that minimum possible time. And the value of n is up to 400. And m is up to n choose 2. Is the statement clear? If you have any questions about the statement, if it is not clear, you can put a minus or say that. If you are clear, please again use the emoji or put a plus in the chat. Use this emoji or put a plus in the chat. Are you all okay with the statements? If there's any issues? Let me see what you're asking if I didn't. I'm not sure. Okay, you're not asking from me. So, okay. So how can we solve this problem? Do you have any idea? We want to find two passes. It's like we want to find a red path. We know that between each two vertices there is either a red edge or a blue edge. So we want to find a red path and a blue path such that they will not visit the same vertex at the same time. They can visit the same vertex at different times. But if they come to the same vertex at the same time, then there will be an accident between them. And you want the maximum of the length of these two passes to be minimum. For example, in here you have a path of length 4 with red edges and a path of length 3 with blue edges. So in here, maximum of 4 and 3 is going to be 4, and it takes 4 hours for both of them to reach to vertex n. So we want two passes. We want to minimize the length of the maximum pass. How can we do this? And there is an edge of one of the colors between each two vertices. Yes, nice, great. That is basically the main idea of this problem. Yes. So the point is, what you're saying is that we say that between each two vertices there is an edge of one of the types. So the point is that, okay, if for each two vertices that is like that, then there exists an edge from 1 to n as well. So the point is that we know that between each two vertices there is an edge. So between 1 and n there also is an edge. There is an edge between vertices 1 and n. It is either red or blue. If it is a red edge from 1 to n, then it means that the bus can only go to n with one step, and it will never clash with the train because the path of the train will have at least length 2. The bus can go from 1 to n in one step, and we just run BFS on the blue edges. And if the edge from 1 to n is blue, you can just say that your train will go from 1 to n in one step, and then we run BFS on the red edges. So the point is that we know that there is an edge from 1 to n. It is of one of the types. So one of the vehicles can use that direct edge. And for the other vehicle, we run a BFS. And we're sure that we won't have a clash. Why we won't have a clash? Because one of them has length 1 and the other one has length more than 1. So one of them will not visit anything other than vertex n just at the beginning. And the other one visits n later. So they will never have a clash. So we just need to know that for one of the graphs, either the red graph or the blue graph, I mean the red edges or the blue edges, for one of them I have a direct path to n, for the other one I run DFS, and this way I can find the answer for this problem. Is it clear? So that's exactly the solution that Ati has discussed here. If you're okay with that, please again use this emoji or say that in the chats. So this is the first problem from BFS that I want you to make sure that you implement it and you accept it. It is not a hard problem. It's just a simple BFS that I want you to do it. And it really helps you to get familiarized with BFS and accept one problem from BFS. That can help you a lot. So that's basically it for this session. In the next session, I think we're gonna have, I mean, the best thing that we can have is to just have a problem solving session in our next session. What do you think? You can also tell me about your ideas. But I think the best thing is to have a problem solving session for our next session, and we're gonna solve a lot of problems. And I think that's gonna help you a lot to understand things better. And guys, if you liked the video, I would appreciate it if you can like the video here or subscribe to the channel. As always, you do not need to do that, but if you do, I think that can help this work to be seen better. And also, I would appreciate it if you share the video with some other people. If you think that there are some people that this video can help them, I think it would be nice if you can share this video with others. And also feel free to, as always, feel free to join our Telegram channel or our Discord server. Our Telegram channel is here. Our Telegram channel is here, and our Discord server is here. As I said, for DSA practice, sources are like Yusaku guides that can help you a lot. We only take shortest level for BFS. Okay. Any tips for constructive? For constructive, I think we can also have another stream for constructive algorithms. How was today's session, guys? If you want to rate it from 0 to 10, I just want to know these numbers to know that what is the situation. So feel free and give me your honest feedbacks. If you want to rate it from 0 to 10, how was this stream? I personally think that it wasn't maybe the best possible. I think there was some issues, but I want to know your opinion as well. Thanks a lot, guys. I'm so glad that you think so. Although I personally believe that there are some things that can become better. I see. Nice. I would appreciate it if you can also put comments in the video. I think that can also work. So thanks a lot for all your feedbacks, and if you had any suggestions, especially if you had any critics, feel free to say them anywhere, in here, in Telegram, in Discord, in CF, wherever you want it. Feel free to tell me about your negative feedbacks as well. I think that would help me a lot to become better. And I think your negative feedbacks are gonna help a lot for me to improve. And I know that there are always easy issues, and the point is to make things better over time. So, what have we covered so far in this series? I've covered DFS and BFS and some types of graphs like bipartite graphs, and passive terminology like passes, walks, and cycles. And also we've discussed undirected graphs, directed graphs, weighted and unweighted graphs. And we have solved a few problems. So basically, I can say that we have covered some basics. And in the next session, we're gonna solve some good problems that are gonna be helpful for anyone around that rating. I will try to put also some challenging problems in our problem solving session so that it can be useful for anyone. But I will use problems that do not need any prior knowledge. So if you are new, you don't need to worry about it. I will try to find problems that the main hardness is to come up with the idea, not need to know. You don't need to know and have any prior knowledge for them. I will also, if it helps, yes, I can also share a spreadsheet. I will share a spreadsheet in Telegram with you for training, and maybe in Discord as well, so that you can do training. I will share some problems that you can solve. When you reach shortest path, you mean Dijkstra and stuff, right? Because shortest path on weighted graph, it's BFS, and we discussed it today. But I think in the next session, we're gonna solve so many problems. I think that the next session is gonna be helpful for you all, because I'm gonna solve problems from different difficulties and problems that need thinking to come up with the ideas of them. And after that, we can move on to the next important topics. Yeah, we will cover things like Dijkstra and stuff later on, after our next session. Okay, thanks you guys a lot for joining today. I'm so happy to have you here today as well. I hope that you have enjoyed this stream and you have learned something in here. So I hope that is true. And I hope to see you in the next live streams as well. Tomorrow we have a CF contest, and I'm gonna do the live stream for the CF contest, and hope to see you there. And in our next topic streams, our topic streams are always on Friday from 12 to 14 GMT. This week, because there was a contest, we did it on Thursday. But from the next one, it's gonna be again on Fridays. And yes, we're gonna also have number theory stream as well. Each week we're gonna have a stream, and we want to cover every topic over the long time, because in the next year we're gonna have 52 streams if we have one stream per week. So we're gonna distribute it over these different topics, and we're gonna cover all of them as you wish. Thank you a lot again for joining today, and if you wanted, and I would appreciate it if you can share this stream with some other people as well, so that others can get help from it as well. See you next time, guys. Bye bye.